specializes in corporate lobbying and harm, conflict of interest, and scientific disinformation. Her in-depth work on the EU regulation of endocrine disruptive chemicals was shortlisted for the Albert Ludre Prize in 2016 and was awarded the Louise Weiss Prize for European Journalism 2017. In February this year, in 2023, the journalists in the Forever Pollution Project collected and aggregated hundreds of databases to establish the first map of the disinformation throughout Europe of PFAS chemicals. Today, Stefan kindly agreed to present and share with us the method they used to map the forever chemicals, the PFAS in Europe. And we're very excited, Stefan, to hear and welcome you in this session. And I'm very pleased that you agreed to participate. Stefan, you have the full floor to share your presentation, and please go ahead. We're waiting to see your presentation and the slides. Thank you.
Thank you very much for the introduction. I'm not sure I'm so familiar with, so I should share my screen myself?
Please, yes, if you can.
Okay.
Otherwise, I can assist you in this.
Okay, I thought it was uploaded in the system. So let me just do this quickly, if I can. Sorry about that.
No worries. I see we have lots of welcoming messages in the chat from Pakistan, from Germany, Bangladesh, Cameroon, Tampa, Florida. Hugh Rodriguez, I see, is joining us. Good morning, Hugh. It's quite early for you. Canada, New Zealand, Australia. So very international conference. Okay, Stephanie, we can see your screen. Please go ahead.
You can see my screen?
Yes.
Okay.
Please put in the full mode.
Yes, this is what I'm trying to do. Okay. Is it good for you now?
It is good for all of us, yes. And I just want to remind all of our participants that this meeting is recorded. If you have any issues with recording this meeting, please let us know in private message. And so after this meeting, we will share all the recordings with you and will be uploaded on our website. Stefan, please go ahead. Thank you.
Thank you, and sorry for this slight delay. I'm very honored to be here, and it's a pleasure to introduce this journalistic work that was like super underestimated in terms of work when we started it. So it's a project called the Forever Pollution Project, and it's what we call a cross-border journalism. Cross-border journalism is a new form of investigation that you probably know through the investigations such as the Panama Papers, but there are also different ways to do cross-border investigations through ad hoc projects that are focused on very specialized topics such as PFAS. And you can see on the screen the number of partners. We had 12 countries and 17 media, and we've been publishing since February. The next publication will be in Spain this week or next week. So what we did is we published this map that you can access freely on the website of Le Monde that shows the contamination, PFAS contamination in Europe through different layers, non-contamination, presumptive contamination, known PFAS users, and PFAS manufacturing facilities. And I'm going to explain how we worked and how this data was collected. So how we started working was we based our work on this very important report where you can find anything you will need on PFAS, as it's a starter's kit. For us, the cost of inaction that was commissioned to Greta Goldenman and her consulting team. And somewhere in this very dense report, you have this table listing 12 PFAS facilities in Europe and a footnote saying we think there might be between 12 and 20 facilities. So our starting point was to locate precisely those PFAS facilities, which was not an easy task, as you know, this team of consultants has spent 1 year working on this and couldn't locate them all. So very quickly, we are just journalists. So we found ourselves confronted to many questions that have to do with the basic chemistry of PFAS and the how you make products and chemicals, and we're not specialized in this kind of thing. So we started listing so many facilities that we thought, there might be something wrong in our methodology. And we we felt the need to ask experts how they would define a PFAS manufacturing facility. And to help us doing this work, we had peer reviewers. Of course, the term is overstated, but this is how we have called them in this experimental peer-reviewed journalism path. And so we asked social scientists, environmental chemists, and also Greta Gorderman, the author of this report that I mentioned, to help us resolve some scientific questions, because we wanted to provide a public information tool that with sound evidence that could be built on, and not crap work, because this was the first map ever, and we thought if this effort is to be done, then it should be quality work. And so we decided so the next step, after we realized there was this 20, maybe 20 facilities, that there could be more to put on this map. And we became aware of the map that was done by an American team for the contamination of the United States. At that time, the methodology paper hadn't been published. So you have a website where the contamination map is available, and with these different layers, including presumptive contamination. And so we've decided to adapt this methodology and stick as closely as possible to their methodology, and adapt this map to Europe. As I explained, we tried to work as rigorously as possible. So every step and every decision we have made are contained in the methodology that is available on Le Monde's website, where every definition and every move and everything we have found and every reference is carefully registered. The first step was to collect data for known contamination sites. To do this, we reached out to regulatory agencies across Europe, but also to scientific teams who had published data or scientific papers in the scientific literature. And for many of them, we had to interact with them, to ask them to send data with precise geolocation or spreadsheets instead of PDFs. So that was a huge amount of work in terms of the time. And in the end, so what you can see on the screen is the kind of the index of all those databases. There are 100 precisely of them, and then there was we had 2 data journalists and a map data journalist to process this data. Ultimately, on the known contamination layer of a map, you can see 17,000 known contamination sites. One difficulty that we had is to determine above which limits we would put the data, because for technical reasons, it is not possible to have hundreds of thousands of spots on a map. So we have decided to only have values above 10 nanograms per kilo, and also to kind of calculate clusters, because there are many places where the values are above 100 nanograms per kilo or per liter, but not all of them can be considered as hotspots, because many of those values were measured around facilities that are known to be contaminating the environment, or military bases that have been contaminated through firefighting foams. So we kind of made a triangulation to calculate a number of hotspots, and we have 2,100 of them. Finally, we think this is the final number of PFAS producing facilities in Europe. There are 20 of them. 3 are not active anymore, but of course, it doesn't mean that the contamination has stopped, because the PFAS contamination is here forever. So Miteni in Italy, Gruppa Azoty in Poland, and Arkema in Zaramillo, that's in Spain. And the Arkema facility is an F-gas facility. And as you probably know, some F-gases are also PFAS, or degrade into TFA, which is a PFAS. So we put F-gases facilitating producing facilities on this list too. Then the second step of the investigation of this work was to map presumptive contamination sites, which was the most complicated task, because the main reason is because we don't have high quality geolocation data in Europe, contrary to the US. So the military sites is something we had to do hand by hand. We had to look up for them in each country. The airports was five seconds research, because there's a website listing all airports. And then we collected firefighting training sites, repertoires that were made in Flanders, Sweden, Norway. And that explains the number of yellow spots on our map. It's because this work on firefighting foam contamination has been done. Then the second category, sorry, I didn't say that. The first category of presumptive contamination sites, of course, is through firefighting foams. The second is related to waste treatment, so that's wastewater treatment plants and also waste management sites. And the third category, which was the most complicated, because for the two previous waste categories there are databases available at the European Environment Agency. And the third category, industrial facilities, was the most difficult thing to do. Sorry. The reason for that is that the US team made a list of 38 industrial activities identified through a code called NAICS code. That's the nomenclature of economic activities. And these 38 industrial activities have been documented as using PFAS and emitting PFAS in 4 distinct sources that are considered reliable. We couldn't make the exact match because we don't have the same nomenclature. So we worked out a correspondence and found 31 NAICS codes. And in the end, that's around 3,000 industrial sites, but that's a complete underestimation. There are many, many more than that. We only took the most emitting industrial activities and above a certain threshold, and those beneath are not on the map. And then in the end, this is how this look of presumptive contamination sites looks like. You've got these different categories, and as I said, you can see the firefighting foam contamination work. When it's done, it's pretty impressive in some areas of Europe. And then there's a third category that was not in the US methodology that we created. It was an intermediate level of evidence category. So these are sites where we know PFAS are used, for example, to customize fluoropolymers, but they don't make the synthesis of PFAS themselves. They buy it, they manufacture their own products, but there's no sampling evidence showing any contamination. So we created this known PFAS users category that the US team is going to add to their own map, because they thought it was useful not to lose the evidence or the knowledge that we've collected, or that they have been collected on this intermediate category. And that's about it for my presentation. You can find all the 75 articles, documentaries, podcasts that we have produced in the past months on the website foreverpollution.eu. Thank you for your attention, and I'm happy to take your questions.
Well, Stefan, thank you very much for this informative and very helpful presentation for us to understand how you did mapping of forever chemicals PFAS in Europe. This is very informative and very helpful. Just to let you know that all publications, all articles of it are already online. You can check out some interesting articles in the newspapers that were published in February and March. I'm just going to post the links after this presentation. So Stefan, thank you very much. I would like to possess the floor and open the floor for the discussions. And if you have any questions to Stephanie, please feel free to do it. Ravi, what do you think? It's a very impressive, isn't it, what we just heard? And we have some chats as well here saying that it's quite impressive work. I'm not sure, I can't see my screen. Okay, now I can, yes.
Sergejus, yes, indeed. Really impressive work, and delighted to see the effort that has been invested to come up with the map that Stephanie has come up with. And it's all about the risk that PFAS poses, not just to the environmental ecosystem, but to human health as well. The key question here is where to from here, because we do know that there are so many sites potentially contaminated with PFAS. What approach is EU taking, and what approach the many countries that we have who are confronted with PFAS are taking? So that's something which is worth looking forward to. From Stephanie's perspective, Stephanie, where do you think this will take us?
I'm sorry, could you say that again?
Where do you think your report will take us now that you've provided a clear picture of the number of contaminated sites, including industrial sites?
Well, our goal was to create a public interest tool that is imperfect. I mean, we are only journalists, as I said. We're not scientists, so we are not. We are very much aware that there can be we had mistakes that we've corrected, and there's more work to do because it's really not a complete vision of PFAS contamination in Europe. So our goal was to provide this tool to create something that could be improved and reused. So the database is available. We are looking for a small budget to add extra data that we could not include in the first data set, which would include the values below 10 nanograms per kilo and liters, and also all other PFAS that were measured, because we only have information for 5 of them on the map. And we have the data for the other PFAS, for example, and it's very valuable for scientists, of course, to have this data. And so what we are, I think our main problem now is that there's data created every day on PFAS. The Spanish team of journalists who are working on the project are currently have gathered like 140 data for 140 sites in Spain. And we would like to integrate it to the map. But the problem is that Le Monde is not a research institute, and we don't have a person who's dedicated to this work and who could work on a permanent basis on feeding the map and adding some new data. So we are, I've been talking recently with CNRS in France. So that's the #1 research institute in Europe, I believe, in terms of number of scientists. And they are ready to discuss on how they could take over the map and maybe add tons of layers, like for other pollutants and other kind of data that could create really powerful knowledge.
Thanks, Stephanie. There was a recent article published in Environment Business Journal based on similar approach that they took in US, and they estimated that the cost of remediating all the sites in US could be as much as $200 billion over 20 years. Mm-hmm. Just looking at that and the number of sites that we have in Europe, just to clean up the contaminated sites would be a massive task financially as well.
Well, I couldn't agree more. At some point at the end of this investigation, I thought I would try to calculate. Of course, that was a little too ambitious for what I could do, because it's a real work to do this kind of things. But I started, doing the math of the known figures about, how much it costs. It costs to clean the water around the Mitteni contamination, for example, for 305,000 people. And at some point, I just decided to stop, because I was above several tens of billions, and it was just what had been spent already. And the figure I've heard in the US from water treatment companies is that it would cost 400 billion to clean the water, just the water. And of course, it doesn't take into account the soil and all the places that are still unknown in terms of contamination. And so maybe it's a very pessimistic view that I have, but I've come to the conclusion that the externalities created by PFAS are the kind of showing that the system doesn't work, because it would lead to the bankruptcy of societies and governments to clean up, if they have to pay, of course. If we consider this PFAS contamination as externalities, of course, if the polluter pays principle is applied, then we're talking about something different.
Indeed, very interesting. I just have a quick question. I see Claudia had exactly the same question as I did in the chat box, but in the quick QA box. Thing that we met Stefan before in February in the HCH conference, where I first learned about the project publications. So we're now mid-June. So 4 months passed since you presented this in February. What was the reaction of not only European Parliament to this work, but also to other perhaps stakeholders or private sector to what you've done? What was the reaction, if you can just quickly summarize in a nutshell, that you received over the last 4 months?
We are trying to keep track of the reactions we use and these kind of things. It's not easy, but we know that the project has been mentioned at the European Parliament. We know through our sources that the project has been talked about a lot at the EU level, at ECHA, at the European Commission, that regulators say it's a very useful tool to start with, and that's something that I think is very remarkable in the follow-up of this work. It's the first time that I do something where regulators reach out to me instead of being angry about my criticism about how the system doesn't work and these kind of things. And I've been invited by the Flemish government for the EU presidency, the Belgian presidency of the EU next year, for a PFAS event in Antwerp to talk about the project also, because they are trying to figure out what is the most interesting in terms of tools in what we have created that could be used for concrete action. And that's something that for me is the most important thing, is that our work is used for concrete action to protect the public as quickly as possible. And so we've seen this EU level thing, but also at some national levels. In France, there were 2 law proposals, several suits that were launched against the companies that have been polluting the most in France. So we have Arkema in Lyon, which is the #1 hotspot in France. So there's a litigation starting with this pollution. So this has created, and also maybe I should mention 2 other things. It's because with this map, you can look, in your backyard. Is there pollution in my village, in my town? And so there's been also a lot of local reporting by the press and reactions by the local representatives to push, to put pressure on the public authorities to, sample the environment, biomonitor the people. And then the last impact I see is that the project is used, the data that I said is available freely on the website of Le Monde, is reused in 10 research projects so far across EU, including a major salt contamination project. And that's something that I have to say I'm very proud of, that it can be used for research.
I guess the most important from this is not to stop, but continue this investigation and map, as you said, other pollutants, something that we need to do within the network as well in the near future. And with our colleagues at the GSP, mapping of soil contaminants is very important. And I'm very glad that you are highlighting this issue globally.
Thank you.
Well, thanks to you. So if we don't have any questions, I think we're just on time to continue to our next speaker. Again, if you have any other questions, please put them in the Q&A box. Then myself or Stefan will be glad to answer them throughout the session. Stefan, thank you very much. And we're looking forward to collaborate with you in the near future and inform on our activities related to mapping soil pollutants.
Thank you.
Thank you very much. Well, Ravi, I guess we're very good
Thanks.
with the next speaker. Would you like to take the floor and
Thanks.
introduce our next speaker?
Thanks so much, Sergejus, and well on time as well. Our next contributor speaker is Dr. Gordon Brinkhurst, and Dr. Gordon Brinkhurst comes from Pure Earth. He brings to Pure Earth extensive expertise that he has as an environmental consultant. At Pure Earth, he serves as the senior technical advisor, and he has been an active member of Pure Earth's technical advisory board for over 7 years. He's also adjunct professor at the University of Connecticut in USA, and here he teaches an undergraduate class on completing environmental site assessments and pertinent regulations. He also serves as a member of the University of Connecticut's Geoscience Advisory Board, and thus he brings a lot of experience into the presentation that he's going to make today. The focus of his presentation is identification and monitoring of lead and mercury polluted soils, and therefore he also underpins our working area assessment and monitoring. Please join me in welcoming Dr. Gordon Brinkhurst and welcome him to his presentation. Over to you, Dr. Brinkhurst.
Okay, thank you very much for that kind introduction, and thank you all for having me. And I'd like to share with you today our work at Pure Earth. Pure Earth has been around since 1999, so about 23 years thus far. And our mission is to reduce children's exposure to currently lead and mercury in lower and middle income countries around the world. Earlier, when we first started, we did other contaminants as well, explosives, pesticides, chromium from tanneries, etc. But then our focus has narrowed in recent years to just lead and mercury. What you're going to be hearing a lot about today is our toxic sites investigation program, which we started in 2011, which is basically to identify toxic hotspots around the world in lower and middle income countries. We've done this and developed the protocols for this over many years with funding from people like USAID, UNEP, World Bank, etc. And again, today we focused mostly on lead and mercury, and we also focus currently as an organization on a broader assessment of lead and mercury exposure sources, including spices, cosmetics, aluminum cookware, and promote blood lead level surveillance work in many of the countries that we work. So our work is much broader than it was initially, but I'd like, since given the topic of the conversation today, focus on the toxic site investigation program. So over the course of our work in the last 24 years, we developed sort of a 13-step process, which starts with identifying toxic hotspots around the world, doing some sort of initial site assessment. And those two portions of it compose our toxic site investigation program, which is, again, the main focus today. And the other steps involve additional detailed site investigations, evaluation of potential risk reduction alternatives, design of a risk reduction or remediation project, community awareness, and then implementing these risk reduction projects, post monitoring and evaluation, and finally long-term site care and management. Again, all of that is not really the subject today, but more of the assessment, the initial site assessment, and entering all of this data into a database. And again, identifying sites of concern, developing data, field data sufficient to estimate initial risks, and also to be able to prioritize sites for further investigation based on public health risk. We use, basically industry standards, prevailing standards and guidelines for doing such work. We rank the sites in order of risk based on the magnitude of the contamination that we're finding and also the population that is exposed. So again, our focus is on low and middle income countries. Why? Because nobody else seems to focus on those at all. So there's a definite need for work in these countries. We generally work with point source pollution, not cars like, you know, lead from leaded gasoline, etc. Pesticides is a slightly different animal, obviously. We do work with pesticides, mostly not with respect to normal application of pesticides, but more pesticide storage, such as legacy DDT sites in the former Soviet Union. So not normal application of pesticides, but more storage and legacy dumping sites. We also focus on toxic pollutants, so not sewage or bacterial contamination. And certainly we work mostly at legacy sites, not active factories, although we do work with some informal lead acid battery recycling sites. And we focus on pollution where it's above international public health standards. And we focus, you know, prioritize sites for further work where there's an actual exposure pathway to the local population. And why do we do this? You know, it was an initial attempt. You know, when we first started, we were more reactionary in terms of people would come to us for a particular site. And we realized that there was no idea of the overall universe of toxic sites in these lower and middle income countries. And we use this information to inform communities, inform governments, prioritize sites, like I mentioned earlier, for further investigation and hopefully some type of cleanup. The methodology we used under TSIP we called it initial site screening. And it's basically sending local investigators out to a site for 1 to 2 days generally to do the work and collect the information. Over the period of our TSIP program, we've entered 5,000 sites in approximately 50 countries. It's, I think, the only publicly available global database of these types of sites, which can be accessed at the website listed here. What does this look like in the world? These are the 5,000 sites. The dots are located, obviously, in the countries that we've worked. They're, again, focused on some of the lower middle income countries. The lack of dots does not mean that there are no contaminated hotspots in those areas. We just haven't been there, I'll say, yet. And again, the focus is on lower middle income countries. So you won't see any dots in places like the United States or Australia. Not to say there's not toxic hotspots there, but other people are addressing those. So what does this look like in a little finer scale? On the left, this happens to be Bangladesh, where we assessed almost 300 sites, the majority of which were associated with informal recycling of lead acid batteries. In the middle are the sites around Dhaka, the capital, and on the right is one particular site, which actually contains way more data than the TSIP database, because we did a detailed site assessment here, and we also did a risk mitigation project at this particular site. In Indonesia, we assessed 154 sites, 50 of which happened to be associated with lead. Many of the other sites were associated with mercury, which obviously makes sense as they do a lot of artisanal gold mining. In our database, we have about 630 sites that are mercury as the key contaminant, which again is a little under 15% of the total sites we've done. Are there more ASGN mercury sites out there? Definitely. This is what our site database in Colombia looks like. I think we were working at a total of 85 sites in Colombia. We follow a risk screening model where there is a pollutant, a migration route from the source to the community, a pathway for potential exposure, be it dermal, inhalation, or ingestion, and that people are actually exposed to the identified pollutants. Again, we're focusing on the initial site assessment, and it's, again, just an initial assessment of the site investigation. So again, we train local groups of investigators. We work with universities, NGOs, anybody who's local in the country who we can train. So we have a team, and we have developed TSIP site screening protocols, and we generally have a 3 to 4 day training with them, comprised of 2 days in the classroom and 2 days in the field, actually implementing what they've learned. And this is basically a 5-part process in the TSIP protocols. The first is actually going out to the site and collecting data such as the site name, GPS coordinates, the key pollutant, and collecting sampling data, typically with an XRF or Jerome for mercury. Physical description of what the site looks like, migration pathways, exposure pathways, how many people are in the area of the site, people who live there, visit there, work there, etc. An initial receptor survey as to drinking water sources, surface water bodies, stakeholder engagement with the community and people living in the area, and finally formal reports or taking site photos. And all of this is uploaded into the TSIP database, and which is accessible again to the public. Again, this is just an initial site screening. It's not a detailed site investigation or risk assessment. This is a page out of our TSIP protocol handbook. And again, it's a pretty long handbook, but it gives the local teams information about the materials required, interviewing, stakeholder engagement, estimating population, how to collect XRF readings, etc. These are generally the tools of our trade, XRF for total metals, and then we use a Jerome or Hermes for mercury analysis in air, or also with jar headspace for soil screening. Again, the beauty of these instruments are the fact that you can collect real-time information in the field, which is it's invaluable in guiding our more in-depth investigations. Just very quickly, what do these sites look like? This is a used lead-acid battery recycling site in Bangladesh, where they basically hack open the cases, take out the lead plates, and you can see in the middle, they've piled up the lead plates atop a coal in a pit in the ground, and they will smelt those into lead ingots that go back into the battery recycling center. They typically get caught in these informal recycling operations and get chased away. And what do they leave behind? They leave behind a mess. These are a pile of separators for the batteries where kids play and as you see, the young girl is playing with the actual separator, which is loaded in lead. This is the map from earlier showing soil contamination in the tens of thousands of parts per million at these two sites. From a conceptual site model, they affected probably about 5 hectares of soil, but it was very thin over the whole area because it was generally through atmospheric deposition. As you can see here, just limited to the first 1 to 2 centimeters of soil. So we did design a risk reduction project here, which involves scraping that upper 1 to 2 centimeters of soil and burying it in a deep pit covered with a geotextile and 1 meter of clean soil. Artisanal gold mining is the largest source, I think, of mercury contamination around the world. Very complicated compared to lead as it transforms in the environment and disperses. And so the sources are not as well defined, but we've done a lot of work. I don't know why that one's blank, but they're messy with huge tailing piles, huge bags of materials that have left behind, ponds, etc. And I'm just sharing some of the pictures of the work we've done at ASGM sites. These happen to all be from Colombia. And this is a map showing concentrations in air in Antioquia in Colombia, which was the focus of this particular investigation. And these are soil concentrations. Again, these are in and around tailings processing facilities where they're extracting the gold with mercury and then burning the mercury off to recover the gold. And I think that's all I have time for. So thank you. I'll entertain any questions that anybody might have.
Ravi, you're muted. We can't hear you. Just before Ravi unmutes himself, Gordon, thank you very much for this indeed very interesting presentation showing what Pure Earth is doing all across the world to treat and raise this awareness across communities for lead and mercury risks. I'll be more than happy to discuss that more and see how we can liaise and collaborate together, specific for those two chemicals, pollutants that you're very knowledgeable, your team is doing. Ravi, do you have any comments?
Thanks, Saj. I don't mute myself. It seems that somebody mutes me. First and foremost, Gordon, that was, yes, absolutely outstanding presentation. And it's really great to see that you have been able to get through to 50 different countries and 5,000 sites. That's an incredible piece of work. And it's quite concerning when you look at the data that you have generated, the extent and severity of contamination that you see, especially where lots of people are living as well. So with that comment, I would like to open it up for discussion and see whether there are delegates who might have questions. So please do raise your hands and we would take it from there then.
We actually have one interesting practical question to Gordon about from Carlo Giacomini, ISPRA, asking, are the portable tools affordable and how much they cost? They might provide a good support to most field research on the spot and with the few recommendations only to follow. Gordon, do you have any comments for that?
I do. The XRF itself costs on the order of 25 to 30,000 US dollars. I believe the Jerome is somewhere in the order of $10,000. So they are very expensive. They are very fragile instruments in terms of they do take some care in the field, but they again are just indispensable. The only alternative is to collect soil samples and ship them to a lab and get in certain results maybe 2 weeks later, and not very useful for mapping out a site.
Interesting.
Yes, and XRF is a great way to assess metal contamination out in the field. And you're right, Gordon, it's a bit expensive, but also in Australia, for instance, you got to have a radiation license and accreditation for us to be able to use it out in the field. So largely because of X-ray radiation as well. But a great tool. Once you spend that much money, it saves you money as well from the assessment perspective. Go ahead, Gordon.
I do see in the chat in terms of blood analysis for health, and that is something we absolutely do, not as part of the initial site assessment work that we do, but associated with all of our risk reduction projects. We collect blood level data before and approximately a year after. And as you indicated earlier, these are sites where kids are running around and their blood lead levels are 45, 60 micrograms per deciliter. They're hugely impacted. And hence the reason for these risk reduction projects, it is about protecting the children predominantly. It is not about restoring the environment to some pristine condition, but basically breaking the exposure pathway to children. And it has been very successful in reducing blood lead levels at our projects that we've worked on.
Indeed. We have another question from our good friend Marco Falcani here in the chat asking, Dear Gordon, are there any other portable instruments that you are evaluating for continuation of the project?
No, there are some cheaper methods that we've worked with Columbia University in terms of lead wipes, which we use for paint, trying to develop a method to use on soil. Again, a low-cost method for evaluating and certain things like that, and with a Dutch company, Lumetalix as well. So I also see that landfilling the battery wastes does not pose a groundwater risk. It does, and ideally, we would love to dig the soil up and take it to a hazardous waste landfill somewhere. Those facilities are generally not available and would not make this a cost-effective intervention. So what we have been doing is adding phosphate, which in the form of fertilizer, essentially, in order to fix the lead and make it less bioavailable and less leachable. It forms pyromorphite over time, and that is our technique for reducing that threat to groundwater. Also, part of our work, we do a receptor survey to make sure of who is or isn't drinking the shallow water in the area of these sites and sampling their water as well.
And Gordon, there is another question here regarding background levels of lead.
Yes, background levels of lead are a very interesting question. In the US, depending on where you are, they can be 10, 20 parts per million. You go to the area of, I worked in Kabwe, Zambia, where there's a lead mine, then, background lead levels are sometimes in the percentage levels. So background is relative. You always have to be aware of what background metals concentrations are, because obviously they are naturally occurring. But usually they're in the low ppm range, tens of ppm. And our standard that we generally work with is something on the order of 400 parts per million. So, but again, in terms of, elevated above background, it helps to take samples, control samples away from the contaminant site.
Thanks. And quite a few more questions here. One is that focuses on your presentation that's all about point source. What about non-point sources like vehicles?
They do exist in along roadways, for instance, from, most of us who use leaded gasoline at one point, there is elevated lead concentrations in those. And so, yes, that is a risk. We did try in the Philippines a number of years ago. Instead of looking at point sources, we collected samples in two residential, commercial areas where we just did a grid and to try to see if there was association with roadway. I know there is, that did not uncover it. So, but it is lower in magnitude than generally point sources.
Do you have anything more, Sergejus?
Yeah, well, the last one from Abdul Salam asking, how effective, maybe how quickly is it to restore cell functions after, I guess, remediation probably? Do you have any?
Yeah, it depends on what the remediation or risk reduction project looks like. If you, scrape and bury soil, for example, and if you were to replace the soil above with a, layer of topsoil, then I think the soil functions return quite quickly. If you cart the soil off and just bring in, non-organic soil, then I think you'd have a much harder time reestablishing natural soil functions for lack of topsoil. So again, it depends what you're doing.
Gordon, when you look at the blood lead level threshold values, it seems to vary depending on which country legislation you look at. And what's your thought about that?
Yeah, it's a good question. So we in the US lowered our number from 5 to 3.5 micrograms per deciliter. But we also are very clear that there's no safe level of blood lead level for the child's developing mind and other health reasons. So lower is better is all I can say. The 3.5, just to be very clear, the 3.5 number is not a risk-based number. Okay,
yes,
it's a threshold value of that 98% of our population is below that number. So it's just a relative number, and that's why it got reduced. So it is not risk-based.
And lead seems to be a major challenge because this takes me to South Australia, Port Pirie. You might be aware and familiar with Port Pirie, and forever they've been trying to see how they could minimize exposure from lead, particularly to children, and they're still trying their best, but children are still very much exposed to lead. What's your thought, particularly from US perspective, children's exposure to lead?
Well, we get exposed to lead from a variety of sources, right? So lead acid batteries and then point sources are one, but more generally, we see spices that are adulterated with lead chromate. We see lead leaching out of aluminum pots and pans. We see lead in cosmetics. We see lead in aeroderics. So there's lead in ceramics, particularly from Mexico. So there's a lot of sources of lead out there. And if you go to IHME data, for example, they mapped out across the world. I don't have that in front of me, what that looks like. And the average blood lead level in some of these countries, lower and middle income countries in particular, are huge. They're over 5, over 10 micrograms per deciliter. And that's not just from point sources. That's from something more systemic than a point source.
Thanks very much. Quite a challenging problem and a challenge that we must take seriously and to see globally what could be done to minimize exposure and, of course, remediate lead contaminated sites as well. So thank you very much again for your presentation, Gordon, and we're delighted that you could join us today as well.
Indeed, Gordon.
You're very welcome. And anybody who would like additional information or help, please reach out. I think you can get certainly my email, and I'm happy to help.
Indeed, Gordon, thank you very much to you and your team agreeing to participate here. I think that we just touched the tip of the iceberg because the questions are on continue in the chat. So if you can stay with us for a little bit while and help us to answer those questions, that will be helpful. But we need to respect the time and go on to the third speaker. And I'm happy to introduce Isabel Wensby. We're now going to Johannesburg. Isabel, good afternoon. Hope you can hear me well. Isabel is trying to share her screen. Isabel, once you're preparing your presentation, let me please introduce you. Isabel is now joining us from the University of the Witwatersrand in Johannesburg, where she is the head of the Ecological Engineering and Phytotechnology program. She has more than 26 years experience in applied research on plant-based remediation of contaminated soils, especially contaminated mine sites in sub-Saharan Africa. Today, Isabel agreed and delivered her presentation on the topic of soil pollution remediation in Africa, guiding us through the recent progress and challenges of soil remediation in Africa. Isabel, I'm very pleased to welcome you, and I give the full control to your presentation. Please go ahead, and we're happy to see you.
Thank you very much, Sergejus, and thank you, everybody. I hope you can hear me clearly. I'm not able to switch on my video as well because we have electricity load shedding here in South Africa, and so we don't have much internet and power at the moment. And I also have far too many slides for you, so I will try to be quick. And also, I am just touching really the tip of the iceberg and showing a few examples today. So if anybody would like further information, please contact me. I've done a brief summary of the sites which I consider to be of significance across the continent, with the exclusion of the Horn and of Saharan Africa, simply for the reason that I didn't have time to collate all the data for them. But a number of sites which are of high priority at the moment would be Sudan, in particular for mercury, with the large mercury spillages that occurred recently in August last year into the Nile River, and of course then across the floodplains of the Nile. Nigeria, both from the oil industry and artisanal gold mining. The Northeast Democratic Republic of Congo, where I do a lot of work in Ituri, and also in the Kivus as a result of artisanal mining of gold and the use of mercury and cyanidation increasingly in that area. South Africa, as an industrialized country with the use of cyanide in gold mining and unlined tailings dams, as they are for most of the continent, and also increasing exploration for fossil fuels, which we are seeing right across the sub-Saharan region, in fact, due to the actions of a number of Canadian juniors and others who are doing exploration at the moment. So these are particular areas which I view as being a priority. There is an excellent project which has been taking place in Tanzania looking at modifying artisanal gold and small-scale gold mining extraction of gold using borax as opposed to mercury, but that hasn't been rolled out across much of the continent at this stage. There is a lot of background information across the continent. There's been a lot of soil mapping exercises at local scales, and there's a huge database of remote sensing information, both multispectral and hyperspectral information, as well as ground-based information on soil mapping and classifications, geological anomalies. And these data are very useful to discriminate between anthropogenic contamination and geogenic contamination of soils. In South Africa, where I'm going to focus on for my phytotechnology case studies, our average annual amount of tailings and coal discards are summarized here. Thank you to my honors classes of a couple of years ago. And these have actually reduced in the case of gold. We were looking 10 years ago at around 250 million tons of tailings per annum. But the gold mining industry is winding down in this part of the world, and there are numerous exercises in recycling the tailings, but still considerable amounts of materials that are being generated. And although I'm using South Africa as an example, please bear in mind that the case studies I'm going to show are relevant really for anywhere in sub-Saharan Africa in a seasonal rainfall environment. These are examples of the tailings dams by the 1960s around Johannesburg. They don't exist any longer. They've been retreated. And in addition, large extensive open cast coal on our prime agricultural lands to generate the energy for mining of gold, of diamonds, of base metals, and so forth. And in fact, the open cast mining of coal and the extraction of coal itself results in the damage of land. And of course, the energy that is required from mining will also result in damage at great distances from the original industry. The physical impacts of tailings dusts are quite wide-ranging. They result in both smothering of vegetation as well as toxicity and salinization and acidification of soils. And this doesn't necessarily result in vegetation dying or animals dying around mines, but it does result in suboptimal agriculture. Metal mobility in the region is exacerbated by erosion, both aeolian and also waterborne erosion, which is in turn exacerbated by El Nino, La Nina cycles and by climate change and more stochastic and extreme weather events. All of these result in the loss of vegetation cover, biodiversity, and soil carbon, and eventually in dysfunctional leaky landscapes whereby metal and metalloid ions can move into groundwater and fluvial systems and wetlands. Within these wetlands, there are concentration mechanisms such as organic sediments and charged clays, but across the landscape, there are also physical concentration mechanisms in a semi-arid environment, because evapotranspiration exceeds rainfall by 2 to 3 times, and that results in the capillary movement of contaminant ions from underground seepage to surface soils and the formation of mineral efflorescence on the soil surface, and eventually redissolution and overland transport. And this diagram from one of our PhD students shows it quite nicely with a tailings storage facility, the seepage of contaminated water from the tailings into the surrounding landscape, evaporation, and the capillary movement of these ions onto the surface of the landscape where they can then be redissolved and move many kilometers away from the original point source. And of course, these can then enter the major river basins. Here we have 2 major river basins entering into the east and the west of the country. And up north, of course, there is the Niger Delta and the Nile River and the Congo River, all massive receiving basins for contaminants from gold, coal, and the base metal industry. On the Witwatersrand Basin alone, over 65% of the tailings dams have failed since 1938. By looking at historical images of tailings dams, and this has resulted in extensive contamination down watercourses. This is actually a 1938 aerial image, and similar scenarios occur right throughout the continent. For example, in the DRC, where I've done extensive work on mapping of Belgian-era tailings dams and spillages in the east. You can't actually see these spillages anymore, they're covered, but they are there. Another consideration is contaminated groundwater. So when we design a planting project, it's not enough to just think about the soil, the contaminated soil or the source, but also what is actually happening under the ground. This, for example, is in a semi-arid area of South Africa, and we're looking across an area here of around 70,000 hectares from the tailings dams I showed in the previous image, where the groundwater is highly contaminated, in some areas to 3 times the salinity of seawater. Around certain point sources, there's also the presence of contaminant ions in solution, not only sulfates and chlorides, but also the uranyl ion as well. So clearly areas that are in need of containment. And one way of containing these massive areas of seepage from point sources is to use vegetation. And of course, also to align ourselves with local governments and developers. Land is in very short supply, especially cleared land, and people are not always aware of the risks that they're going to be exposed to, both respiratory risks and also risks as a result of consuming foodstuffs that have been grown in contaminated areas. And I'm not going to talk about bioaccessibility in edible plants today. I'm just purely going to focus on phytotechnologies. So plant-based technologies, where we want to look at converting mine waste and polluted soils into some form of ecosystem service in order to provide the basis of a new economy. Because if we can mainstream contaminated soils into the economy, we can take pressure off undisturbed lands and avoid destroying even further biodiversity. The types of ecosystem services that we would be looking at would be fuels, pharmaceuticals, and so forth, all using ecological engineering principles. So conferring function and structure on a landscape through patterned and appropriate planting of vegetation. This is a rather nice example from Wismut in Germany. This picture was taken in 1990. This picture was taken more recently, as you can see, and the landscape has been transformed using ecological engineering principles. So using both soil capping, impermeable layers, permeable layers, patterned vegetation, and erosion barriers to control the flows of water and exert hydrological control around the site. And this is quite a nice example of what can be done. Of course, it is extremely expensive to undertake these exercises. We're looking at far more low-key and expensive activities here in Southern Africa. So both harnessing plants and organisms such as avascular mycorrhizal fungi, nitrogen-fixing bacteria, and these exert controls on the rate of both nutrient cycling in the rhizosphere and also contaminant cycling. So they can slow the rate of contaminant release from a point source into the wider environment. And there's a range of these technologies prefaced with the word phytoremediation, phytomining, if we're looking at the extraction of metals. But all of them have the aim of converting mine waste and contaminated soils into a safe resource, a resource where we can have various low impact or even moderate impact activities and not be exposed. Ultimately, even polluted land and polluted water has value, and so we cannot rule it out of the production chain. It's very important to bring it into the circular economy. This is a conceptual diagram showing a tailings dam or a landfill, the use of vegetation to abstract water and exert hydrological control to minimize seepage into the surrounding landscape, stabilize erosion, and mobilize contaminants within the rhizosphere. On contaminated lands, we look at a somewhat different strategy. We'd there be looking at extraction of contaminants from the substrate and removal into harvestable biomass so we can actually clean the site. This is a landfill site on the eastern area of Johannesburg. It used to be a number of old mining pits. It was then backfilled. There was attempts over the years made to grass it, but the area was very degraded, was continually seeping. And this was an example of the vegetation that was achieved using a variety of different indigenous trees. Now, obviously, one doesn't just go straight out and plant. One has to use tolerant material that's isolated from polluted areas, screen it for many years. What you're looking at in this particular image, which was taken off Google Earth last year, is the culmination of about 15 years of research before a tree is even planted in the ground in order to optimize which species, which groups of microorganisms, and how that vegetation is going to be managed on the site in order to contain seepage in the long term. This is another example of a gold tailings dam footprint after the mine dump has actually been removed and reprocessed, and it's continually seeping into the river, in this case, the Vaal River in South Africa. It has very high manganese loads, uranium loads, and a number of other trace elements. It's extremely acidic. We're looking at a pH of about 2.3 in the soil and highly saline. So clearly it requires specialized forms of vegetation. There's also a lot of explosives residues and cyanide residues in the footprint, but both of those can act as a fertilizer for suitable tolerant species of trees and shrubs. And this is an example of some of those planted across this particular footprint. And further pictures, mature trees. In this picture, we've got vegetation that's about 15 years old. So all of these tolerant species of shrubs and trees have been isolated from contaminated lands, propagated using cuttings. Their germination cues have been optimized. They have associates on their roots, such as mycorrhizal fungi, that have been isolated from the same contaminated soils before they then get planted out onto sites. So we can be very confident before we go to a site that the vegetation we're going to use is going to tolerate conditions because it's already been naturally colonizing analogous sites. A key principle in phytotechnologies is to control the movement of contaminated ions, both metals and metalloids, and in particular sulfates into groundwater and in the movement of groundwater into streams and rivers. And in this particular case, we use a strategy loosely known as phytostabilization, which is the use of vegetation to increase evapotranspiration, or ET, over seepage plumes around the tailings dam. This is an example of a site in the process of being planted in order to increase evapotranspiration from around 700 millimeters per year to around 1200 millimeters per year of water to exert a continuous upwards hydro gradient on the plume around that tailings dam. Once again, before one puts a plant in the ground, it's a culmination of many years of research, in this case of about 12 years of a full rotation of different species in a typical forestry site species trial to investigate which species would be suitable, whether we should use local ecotypes or non-local ecotypes. And here's a nice example. These are the same tree species. They're replicated across the site. This is a local ecotype tolerating the conditions, and to its right is a non-local ecotype, clearly less tolerant to acid mine drainage and the saline and contaminated soils. So not only species, but also ecotype screening is extremely important. This is an example of the types of vegetation one would look at using. It's the plants that naturally colonize contaminated lands. We've done large surveys on the gold and uranium lands in South Africa. Others have done surveys on the copper belt, Lubumbashi, for example, the University of the Copper Belt, University of Lubumbashi, both have done extensive surveys in their areas as well. So there are large databases of information on tolerant vegetation that will cope with these polluted areas. Plants need water. We can't implement phytotechnologies unless we have adequate water. So it's absolutely critical to understand the water use of the vegetation types that are being planted. And not only that, will they be resilient and how will they perform in the face of consecutive El Ninos and in the face of climate change and stochastic rainfall and catastrophic droughts? Over a period of about 15 years, we've been measuring the water use on different types of contaminated land, both acid mine drainage and also contaminated soils of different types of vegetation. So ranging from reed beds through to salt hyperaccumulating trees like Tamarix osnoides, the Tamaraceae are North Africa and also across Asia, a very important halophyte tree for remediation. Various species of indigenous trees and of commercial forestry species, both under stressed and non-stressed conditions. So under water stress, where there's no salinity or very high salinity and acid mine drainage, and clearly they use far less water and they're far less effective at controlling the plume under those conditions. Once one has a good understanding of the micrometeorological measurements and the water use through doing long-term trials, one can then do simple models at first in order to estimate the areas of trees that would be required to balance, for example, acid mine drainage runoff and seepage from a tailings storage facility. And this example is from a large tailings storage facility. It's about 484 hectares. We know that it releases just over 500,000 cubic meters of seepage annually. We can assume that the annual is about 400 millimeters more than the existing degraded grassland. So we therefore require about 137 hectares of trees to balance seepage in order to have that driving hydraulic gradient and maintain the vegetation in a slight water deficit, but not so much of a water deficit as to lose the trees over a dry season. These are prospective geohydrological models of the tailings dam itself, and then of the tailings dam with no control, seepage running into the river, based on actual data and interpolation between boreholes, and simulated for 15 years of running a woodland of trees with that increase of 400 millimeters to control acid mine drainage. And then we plant. So these are pictures of actual exercises on the Witwatersrand Basin, where we've put in over, I think it's about 3 million trees probably to date, mostly indigenous, to control seepage from gold tailings dams. Our biggest challenges in this environment are both fire and also the felling of trees for timber, and political will, in this case, from the mining companies themselves. Because trees grow slowly, they don't just spring out of the ground and provide hydrological control within 3 years. It takes between 5 and 15 years for full hydrological control on site. On this particular area, I'm showing where large plots have been planted next to the tailings dam. Very simple planting, whereby we've modified commercial planting techniques using a typical pit planting technique with a super absorbent and starter fertilizer, tolerant planting material on the area, follow-ups for fire control and weeding and maintenance. These are trees about 4 years of age and slightly older with some of my university colleagues, all growing on these previously very barren and degraded acid mine drainage polluted sites. And of course, over time, as soil conditions improve, as a result of the complexation of contaminants in the rhizosphere, grasses and herbs and forbs start to enter the sites.
Isabel, can you wrap up, please, the presentation? Thank you.
Okay. Sorry, I can't hear you.
Can you wrap up the presentation? We're
I'm
quite
wrapping
time
up.
constrained.
And
Thank
then
you very
over
much.
time, measuring the success of these sites is done using a combination of methodologies, both using the levels of groundwater and also looking at the salt uptake by salt hyperaccumulating trees. For example, the Cretohalophyte, Tamarix osnoides, its water use, and the amount of salts it actually removes, not only total sulfur, but also a number of metal ions. And finally, utilizing geophysical methods to determine the removal and the containment of contaminants in the routing zone. I'm not going to go through metallophytes because we've run out of time, but there are a few slides here on using plants for hyperaccumulation of nickel and cobalt from contaminated soils, also from work from a number of researchers in China, which we're also using here, terrasphatate for hyperaccumulation of arsenic. And I won't go through the costs. You'll be able to see these later and wind up. Thank you. Any questions?
Isabel, thank you very much for this indeed very interesting presentation. I do apologize for interrupting you, but we're quite limited with time constraint to respect other participants.
No, that's fine.
Thank you very much. Once again, you've highlighted very clearly the important issue of the pollution in this region in Africa. And I really like the fact that how you emphasized the relationship between soil and what we need to look under the groundwater itself, because both of them, those two compartments are very well interlinked. And that's something that we're going to discuss at the INSOP. And I'm sure we can collaborate together in this topic. I feel your knowledge and experiences will be very valuable for us. And phytotechnologies that you presented are very important to look at in details and implement them in different regions. Because of the time constraint, Isabel, we do have a lot of questions on chat, so I would definitely ask you to please help us to answer those questions if you can. Just one question to you, though, online from our colleague in FAO Ukraine, Tifen Lucas, who is here participating. Interesting question. Is there any successful experiment with biofuel production using thermochemical conversion of heavy metal contaminated biomass? Isabel, do you have any comments to answer this question, perhaps?
Yes, I do. I actually wonder if you maybe have read a couple of our students' papers, which we published recently last year on exactly this, in fact, on looking at the conversion of biomass from acid mine drainage contaminated sites and also explosives contaminated sites to use together with the high ash coal in power stations. So what I suggest you do is drop me an email and I can just forward you those two articles and the other research that is in fact being done on this.
Perhaps you can forward that to me, and while we wrap up the meeting, in the meeting reports that will be shared with all of us after the session, hopefully next week, I can include that as a reference under your presentation so that everyone can look at it. Thank you very much. We have a couple more.
Just to emphasize, generally timber has low levels of metal contaminants. So metal contaminants tend to be concentrated in the rhizosphere and in those plants that do accumulate in the foliage. And the timber itself tends to meet EU regulatory standards. So even prior to conversion.
Okay, thank you. Thank you for your answer. We have some questions, Isabel, for you in the QA box. If you can help me to answer those questions, I think you will be the best expert to look for it. That will be very helpful. Well, ladies and gentlemen, thank you very much for Isabel, specifically to you for dedicating some time for it. With this respect, we're moving to our next speaker, Professor Ravinaidu. Would you be able to introduce our next speaker, please?
Thanks so much, Sergejus. Unmuted, that's right. The next speaker is Professor Minghung Wong, and he's going to present to us on soil pollutants, food contamination, and health effects. By way of introduction, Professor Wong, I believe, is #1 most highly cited researcher from Hong Kong, China. He has global recognition on the work that he has done on environmental pollutants, both from fate and dynamics perspective, as well as exposure pathways and the risk that pollutants pose to human health. I was delighted that despite his heavy schedule, Professor Wong has accepted our invitation, and right now he is with the Southern Federal University and Education in Russia. Ming, I would like to invite you to take us through your presentation, and thank you very much for being with us today.
Thank you very much. I will try to share the screen.
Okay, yes, Professor, we can see your screen.
Yeah, okay, that's good.
Yeah, it's full mode. Please go ahead.
Okay, first of all, I would like to thank the organizers for inviting me for giving this talk, and also Rafi for recommending me to give this topic. Now, afterwards, I thought it's a very challenging job to give this topic within 15 minutes. Now, what I would like to do is to highlight some typical contaminants which I have worked with for the past years, to cite some examples about typical contaminants which related to human health. I'm from the Soil Health Laboratory, Southern Federal University. At the moment, I'm involved with a project, a mega project, supported by the Russian government, and the group leader is Professor Tatiana Mikina. Now, her group has been doing a very good job, so she has received a lot of attention for the past few years. Now, soils are very valuable and yet very vulnerable natural resources, because soils support food and fuel production and possess other functions. Unfortunately, human activities have created various waste and chemicals polluting them. A good example is the National Soil Survey conducted in China in 2014. And the results showed severe soil contamination with all these heavy metals, hops, notably pesticides and PAH, well, especially in farm soils where crops are grown. Now, between 2000 and 2003, I was lucky enough to participate in this global project entitled Regionally Based Assessment of PTS, serving as the coordinator of Central and Northeast Asia. So at that time, we have to be very patient because we did not have enough information, and more important, people are using different techniques in analyzing the toxic chemicals and the way of presentation. But we were very shocked to know the results of two major laboratories in New York, I think. They found out there were a wide range of toxic chemicals. Now, the exercise we had for the regionally based assessment, we did complement the Stockholm Convention of POPs, which enacted in 2001. So at that time, there were the dirty dozen, mainly the chlorinated hydrocarbon pesticides, DDT as a typical example, and also other chlorinated hydrocarbon pesticides, and two industrial chemicals, including PCBs and also HCH, which is also a pesticide, and two unintended byproducts, namely dioxin and furans. So we were very amazed to find all these toxic chemicals in human bodies. And yet, in the Lancet Commission on Pollution and Health, there were more than 30 experts in the world working on this review, and they pointed out pollution is the largest environmental cause of disease and premature death in the world today. So chemical pollution is a great and growing global problem. Few years later, we were commissioned by the Drainage Services Department in Hong Kong, looking at the removal efficiencies of a wide range of toxic chemicals, all these chemicals in 2 different types of soil treatment plants. Now, to cut the story short, not all the toxic chemicals could be fully eliminated. Well, some may be changed into more toxic forms, which I would not mention because of the time. Now, eventually, these toxic chemicals will enter into our food chains. Now, I would like to present you with some of the case studies which are involved about all these toxic chemicals, soil contamination, and human health impacts. The first one is fluoride, which is considered as a geogenic source. Now, this fluoride, because of the brick tea, a poor quality tea made of old leaves, which contain a very high concentration of fluoride. Now, this particular brick tea is different from the typical leaf tea, which usually consume. Well, they usually contain young leaves. No problem for those tea leaves kind of drinks. Now, tea is usually grown in acidic conditions around pH 5 and very often lower than pH 5, where aluminum silicates are dissolved easily and fluoride is taken up actively by the tea plants and deposited in old leaves. And that is the problem. So the Tibetans in Sichuan province, a province in China, developed fluorosis after drinking this tea for a long time. Now, the second case is more common because people in a number of countries are exposed to arsenic-laden drinking water and develop arsenicosis. Now, high arsenic in their food, especially rice, also contribute to higher oral intake of arsenic. A newsletter issued by FAO in 2007 stated that arsenic in rice would pose health risk. That is because paddy rice plants are submerged in water most of the time. Arsenic 3 and 5 are predominant and actively taken up by the plants and deposited in rice grains. This would pose a severe health threat to people of many countries with rice as the staple diet. Now, the third case would be about mercury and fish contamination. Now, fish is grown in coastal waters in South China and also other countries, I believe. So we investigated whether there would be active mercury speciation in the sediment under the fish cages. Because the sediment contain very high organic matter because of the accumulated unconsumed feeds, because we tend to overfeed our fish, and also the fish fecal material excreted by the fish would provide a chance for sulfate reducing bacteria to transform the inorganic mercury to organic form, such as methyl mercury, which is highly toxic. Typical example is the Minamata disease. Now, we also found out at that time that fish feeds are highly contaminated because trash fish, those small without much commercial value, this fish, they are often contaminated, and even the compound feeds because of the protein powder made from the trash fish. Now, it is recognized that fish is the most common route of mercury exposure, not only in South China, but in other different countries like Spain, Turkey, Poland, and so on. The most important thing is mercury could be passed to our second generation through placenta transfer and lactation. Now, the adverse health impacts was demonstrated by long-term collaborator, Dr. Leung, who was the former director of the IVF Center in Hong Kong. So throughout the years, he proved that the frequency of fish consumption and the number of two emigrant led to higher mercury body burdens of the subfertile males in Hong Kong, affecting the sperm quality and leading to lower fertility. I have to add some information. Dr. Leung was one of the two medical doctors who delivered the first test tube baby in Hong Kong in 1986. Now, recently, we published a review and observed that in addition to mercury and lead, the two neurotoxins, POPs and some emerging chemicals such as phthalates and bisphenol A also play some roles causing autism. Now, the first Hong Kong total diet study report on methyl mercury conducted by the Food Safety Center warned women aged 20 to 49 that dietary exposure to methyl mercury would be a health concern after analyzing a large number of food items. So apparently, high mercury concentration because of the large fish, in the food items like tuna and swordfish would be a concern. We then investigated the contents of pesticides, DDT and HCH, and PCBs in human milk of two major cities in South China, Hong Kong and Guangzhou. 7 million, 10 million of population. There were high concentration of pesticides, but lower PCB in these two cities compared with some countries. This is due to the high background levels of pesticides because China used and produced large quantities of pesticides in the past, in 1960s to 1980s. It was then demonstrated that patients with uterine neomyomas, a kind of tumor, contain significantly high POPs and mercury in their adipose tissues than healthy females. Again, we had assistance from Dr. Leung, and also I had a PhD student who was a qualified medical doctor from the mainland to look at this problem. Now, e-waste is a global problem, especially when China banned the entry of e-waste a few years ago. So the e-waste has been diverted to other countries, repeating the same mistakes we made in China. There are several primitive cycling techniques used in collecting valuable items, especially the precious metals like gold, silver, and platinum. Now, among these operations, open burning and melting electronic boards and strong exits are the most destructive to the environment due to releasing toxic chemicals into soil, air, and water. All these different toxic chemicals are generated in the site, and the site acts as a toxic transformer. A good example is the extraction of copper inside cables by burning the PVC outside. That will enhance the generation of dioxin because copper will act as a catalyst. Now, we were one of the very first group looking into the problems. Well, if not the first group, try to be a bit modest. So we have carried out a food consumption survey followed by a food basket analysis, trying to quantify the oral uptake of toxic chemicals. We noted that dietary exposure is the most important exposure pathway with significant correlations between exposure of these toxic chemicals, dioxin, flame retardant, heavy metals, and so on, and high body burdens of the residents and workers. We analyze different human tissues. Now, the epidemiological data from the Center for Disease Control and Prevention also proved that there were abrupt rises of several major diseases like digestive system, malignant tumor, cardiovascular system, and so on. Now, more recently, an attempt has been made to study microplastics and associated toxic chemicals in soil. A project collaborated with Jinan University in Guangzhou, where I also served as a visiting professor. Plastic mulching and using contaminated fertilizer and irrigation water are significant inputs of plastics in farm soils, affecting crop growth. we then published a few review papers about the adverse effects of microplastics, including this one about global status. Now, at the Education University in Hong Kong, we have also embarked on a relevant project on microplastics in the Deep Bay area, focusing on microbeads and microfibers. There is a high uptake of these tiny microbeads and microfibers by bivalves, including mussels and oysters. Now, oysters are very important in southern part of China, posing potential harmful effects on humans. We also found out that the hybrid garoupa, a very popular fish cultivated in the area, and then they contain very high concentration of microplastics in their intestines and stomach.
Ming, how close are you to?
Oh, almost finished.
Thanks
I'm
so
sorry.
much.
Okay. Now, in addition to the tiny particles, we also exposed to toxic chemicals, all these phthalates, bisphenol A. There are additives, plastic sizer, and also the constituent of plastics. So we are exposed to these contaminants because of during food production, packaging, and so on. Another example is the release of bisphenol A from baby bottles, which was a big issue some years ago. Now this is a diagram to show the effects of microplastics and associated chemicals. Now, chemicals management would be an important issue to safeguard environmental and human health. Some years ago, well, 2012, we published a draft guidance on behalf of UNEP about the emerging chemicals management issues in developing countries and countries with economies in transition. We focus on a wide range of all these potential toxic chemicals, and according to the study, heavy metals and PAH were the most concern in these countries, although we also look into some emerging chemicals of concern. Now, 2 months ago, I checked the UNEP website and found 11 chemicals or groups of chemicals with emerging evidence indicating risk. Now, most of these chemicals were the same as in our previous study. Now, the last slide. So what I would like to do is to make some recommendation to we should manage soil sustainably, guard them against from human activities. We should manage all these toxic chemicals, especially the emissions and usages, but somehow international cooperation would be necessary, like the e-waste problem. We should understand a bit more about the geochemical cycles of food contaminants, especially the speciation of these toxic chemicals. We should clean up contaminated sites for crop and fish production. We should ensure toxic chemicals are not used during food production, food processing, preparation, and so on. And we should also reactivate local agriculture and aquaculture safe and quality food production, at the same time to cut down footprint and carbon emission. Thank you very much.
Thanks so much. Thank you so much, Ming. Great presentation that captures containments of concern, and through case studies, you have also demonstrated to us exposure pathway scenarios and what exposure leads to from human health perspectives. Noting that we are constrained for time, we'll open up for one question. Is there a question out there that you might like to ask? Over to the delegates who are present with us.
We have Professor Ming, thank you very much indeed for this fantastic presentation. You highlighted once again how soil pollutants affect our health, showing those different case studies. We have very interesting question from Beatrice Amanda Watts. I'm not sure, Beatrice, if you're interested, you can raise your hand and we can unmute yourself, and you can ask the question directly. If not, then I will ask that question on behalf of Beatrice. Professor Ming, given the pervasive nature of soil pollutants and their impact on food safety and human health, what measures can be taken to reduce the exposure of vulnerable populations to toxic substances, particularly in regions with high levels of contamination?
This is a very difficult question, because there are different scenarios in the world, and also different soil types and so on. I think this would be a difficult question to look at, but I think it's very important that each country should tighten up the environmental protection regulations and so on. A good example is about electronic waste. Now, people tend to take an advantage of the low income countries, that they have a more relaxed environmental legislation and so on. So they dump their waste into these countries. I think we have to look at this problem. E-waste is a very typical problem.
Yes, indeed. And last question from Bayan. That will be the last question for this presentation. Bayan, please go ahead. I'm very happy to see you again today. Please raise your question.
Thank you very much, Sergio. And thank you very much, Dr. Ming, for the very interesting presentation. Actually, my question is about arsenic contamination. What is the level of arsenic in the soil that we might consider as a natural concentration in general? Noting that the US EPA screening levels has put the screening level for arsenic at 0.6 for residential area and 3 for industrial area based on risk. And most areas have an average of 2 to 3 milligrams per kilogram. So I would really appreciate your insight regarding this point. This is my first point.
Okay. The actual concentrations, I don't recall at this moment. I think that's important. I remember a few years ago when FAO issued that warning in 2007 about the threats of arsenic in rice, and then our colleague in China, Professor Yongguan Zhu, they had a panel and tried to set up the upper limit of arsenic in rice. I think that would be a good start about all this arsenic problem. Well, in addition to that, I don't think I have any more comment right now, but I would be very happy to look at this problem and talk to you later on.
Thank you very much. May I have another question also, Sergio?
Okay.
Can we ask that question in the Q&A box, and Professor Ming can address
Sure.
it?
Yeah.
Thank you,
I
Bayan.
would be happy. I would be happy to answer anything by email.
Thank you very
Professor
much.
Ming,
I would
Professor
really
Ming, we will
you can
definitely.
share, yeah.
Okay.
So we could also have Mahmoud Rahman to help you with that question. As Mahmoud has published many papers on arsenic in Bangladesh, and indeed in a number of countries, from background to all the way to contaminated sites. So Mahmoud, you may be present in today, and you might like to respond as well at some stage.
Yes.
So with that, we thank Professor Ming Wong, and over to you, Sergejus, to take us through the next presentation.
Thank you, Ravi.
Okay,
Yes,
thank
indeed,
you
because
very much.
Professor Ming,
Thank
thank you once again for your participation, because this topic specifically will be addressed in one of our working groups, food quality and human health. This is something that we really want to focus this year and the following year. Well, ladies and gentlemen, with this in respect, I would like to move on to our last speaker. Last but not least is Sasha Koishima joining us today. Good morning, Sasha. I hope you're doing well. Well, let me introduce Sasha. She is our Deputy Director of Land and Water Division. Sasha has nearly 30 years of experience in international assistance, policy development in agriculture, water, and environmental and natural resource management, as well as land restoration. She serves in various steering committee in agri-environment of OECD and UNEP Global Partnership on Nutrients and Circular Economy, mentioned the least. And today, Sasha has been working on the idea of this One Water, One Health approach, where she's looking on how water is useful in all its forms and its interlinkages with the environment, food production, and public health. Today, Sasha has kindly agreed to present us and brief us all about One Health approach and find this link between water pollution, soil pollution in One Health approach. Sasha, we're very pleased to see you participating today, and we're looking forward to your presentation. The floor is yours. Thank you.
Thank you very much, Sergejus, and good afternoon and good greetings to everyone. This earlier discussion about arsenic is quite interesting, since it came from my work in our division in the past. And I just want to give a little introduction to our FAO Land and Water Division. Currently, our strategy is to ensure that land, soil, and water resources are wisely used, conserved, and restored for sustainable and resilient agri-food systems that support food security, nutrition, and human well-being. So one of our strategic directions and objectives of the division is pollution prevention and integrated solutions. Therefore, the soil-water interaction to protect human and ecological health in the environment overall. The work that we have done in arsenic was one of the seminal points in which we looked at this integrated way, where inorganic arsenic species is more toxic, and they're made bioavailable through the rocks formation in certain geographical locations around the world where there's high concentration of arsenic, and therefore made available through groundwater boreholes. So through the oxidation process, these inorganic species have become available through irrigation water and absorbed by the plants. So this whole One Health, One Water concept and initiative, and also interfacing with soil and land issues, have been seminal in our work. And therefore, this One Health approach, working with WHO, we've had decades of interactions and experience. And more recently, this One Health approach has become more prominent, made principally by the COVID, by avian flu, so forth in recent years. And so the One Health has been promoted and recognizes that human and animal health, as well as crop and plants, and the wider environment are closely linked and also interdependent. The One Health approach enables the mobilization of multiple sectors, and that is across the health sector to agriculture to irrigation managers to other soil scientists, and all these across all these disciplines and communities to work together to foster this well-being and tackle the threats to health and ecosystems while addressing the collective need for clean water, clean soils, our natural resources from the agricultural standpoint to produce safe and nutritious food while tackling other actions such as climate change and contributing to the overall sustainable development goals. Next slide. Through this One Health information support system, the 4 organizations, the FAO, the World Health Organization, UNEP, and the World Organization for Animal Health have formed this quadripartite agreement, if you will say, to enhance the One Health intelligence to strengthen global health and also security. Next slide. The one environmental on environmental pollution issues, our division, the Land and Water, is the lead coordinator for FAO. And we work with UNEP on pollution prevention control under our joint MOU, Memorandum of Understanding. We're also part of the UN water mechanism that is across over 20, 30 some organizations to jointly work with UN on a number of key issues that are cross-sectoral and cross-cutting across UN mandates. So we're moving not only from the science, but also to the policy and how we can guide our member countries to develop the policy guidance. I heard earlier question, how do you address these issues, not from a chemical by chemical standpoint, but a collective by classes, and so we can reduce the risks to our society. In the past work, we have co-produced health guidelines, for example, of wastewater reuse in agriculture and aquaculture, and also the gray water reuse with WHO and UNEP. This is to address water scarcity and also to address disease prevention, public health principles, using risk-benefit approaches for assessment of a tolerable risk that is tolerable. 1 in 10,000 per population, or 1 in 100,000 population, depending on that particular chemical or pathogen. These are guided for health targets. And the reuse of biosolids, for example, in wastewater treatment systems, the solid part, the sludge, and the recovery of nutrients such as nitrogen or phosphorus are important for food and agriculture as fertilizers for promotion of the circular paradigm, which is another policy from the European Union on the circular economy to strive at resource efficiencies. Next slide. So the One Health approach aims to bring awareness raising by improving key stakeholders' understanding of the linkages between agricultural practices, the water and soil quality, and food safety. And second, capacity building across governments, across science and farmers to enhance innovation and developments of what we've learned today on water, soil quality, and also bring the latest in surveillance strategies for improving food safety. And third, global collaboration, and such as this event and many others that we work together to facilitate information and data sharing globally. Next slide. And according to recent estimates, giving you an example is the antimicrobial resistance. This has also been given high profile within FAO programs. Due to the fact that 1.2 million deaths are directly attributed to drug-resistant infections globally. And by 2050, estimates are up to 10 million deaths could occur annually. And so antimicrobial use, either in animals, human use, or spraying on croplands, the fungicides and so forth. These may cause resistance to antimicrobials in the environment. This is fueled by inadequate waste management guidelines permitting of wastewater treatment systems from human waste. All these are combined to enhance this AMR resistance buildup in the environment. And the global community is increasingly recognizing that our natural environment is an important reservoir of AMRs, and that measures must be taken to address this risk. Next slide. So antimicrobial resistance genes, their fragments and microorganisms are considered the main driver for this rise of AMRs in the environment and in soil, in water. In the graphics to the right, you can see various pathways, pollutants, and also antimicrobials could result in the environment. Of the particular concern that the quadripartite has been addressing is looking at point source pollution. So how do we address, prevent discharges of both treated and untreated human and animal excreta, and that includes livestock, concentrated livestock operations, and these excreta into the environment. Discharges of chemical wastes, pharmaceutical manufacturing, and disposal of unused and expired antimicrobials add to these pollution concerns. So we're tackling wastewater and also the point source pollution areas across all the organizations, and also manure applications. When I mentioned about the reuse, some areas may reuse the biosolids, and how can we ensure that these are treated prior to spreading back onto the field. Other pollutants of emerging concern, we have heard from earlier presentations, organic compounds, PAHs, and so forth. And some of them are regulated and many are not regulated because they're very expensive to regulate. And so the best point of entry is prevention. Next slide. The quadripartite organizations are trying to strengthen, I mentioned earlier, our information systems. We're collectively developing awareness campaigns across all the different sectors, and also allowing better access to necessary resources that will help reduce antimicrobial use in food and agriculture, and to promote the responsible use of antimicrobials. We also provide support to governments in regulatory frameworks for addressing pollutants as classes and compounds, and policy incentives to promote responsible use and take back of antimicrobials, as well as other forms of incentive mechanisms for other chemicals. We are trying to address pollution control points. What I mentioned about the point source pollution, and antimicrobial residues present in waste and agricultural production, as well as pharmaceutical manufacturing of human pharmaceutical products, and also resulting in human sewage. And we are, the fourth one is the application of innovation. Currently we're applying a lot of the developments in whole genome sequencing to track pathogens and also the gene fragments from environmental sources to food, to ensure food safety and quality, and to prevent disease and problems in human health. So the whole genome sequencing is very powerful tool. If there is an illness coming from a cluster of populations or in diverse areas, through the genome sequencing, we can point down to exactly the farm that is causing that particular problem. Next slide, I wanted to go into some of the overarching work that the UN system is working on in pollution, in promoting a pollution-free planet. And this transition is work in progress. And the goal of this is to strive at a pollution-free planet for health and well-being of people in the environment, where there's the right to a clean, healthy, and sustainable environment for all. The impact areas in the next slide. are the areas of influence where long-term systemic change is expected and that can be achieved. That is people-centric, that's planet-aware, and that is inclusive. So the people is focusing on the protection and promotion of human rights, the health and well-being of individuals, groups, and communities. And second, for planet, focusing on the maintenance and restoration for healthy and productive ecosystems to support life on Earth and to provide valuable resources for society. And third, leaving no one behind. This whole concept have to be inclusive for sustainable growth and development, and emphasizing the importance to foster economic and social transformation that balances the short-term needs of today's generation with the longer-term needs of future generations. Next slide. The 10 principles and approaches are addressing principally the real declaration for environment and development, the real principles. In particular, these are intergenerational equity, I mentioned, participation, access to information, understanding that every member states should look into polluter pays principles, as well as precautionary principles in their law and their writing of the laws and regulations, and leaving no one behind. In addition, these are human rights-based approach. The focus should be on prevention. It's safer, it's easier, it's more cost-effective. Second, science and evidence-informed decision-making and promotion of circular economy, because we just don't have infinite resources, and also understanding the One Health approach, the nexus between human, animals, and the environment. Lastly, the slide shows the 11 objectives of this UN Common Approach to Pollution Prevention, is to protect and exercise the human rights, generate information available to all, development of implementation of legislative, regulatory, and policy frameworks and plans of action to address all forms of pollution at all scales, international, regional, national, and local, and prevent and reduce pollution associated with humanitarian action caused by conflict, man-made natural disasters, and emergency response. Fifth, protect the vulnerable ecosystems and to restore damaged ecosystem from pollution. We are in the decade of ecosystem restoration, where FAO and UNEP co-leads this decade to manage ecosystems for pollution prevention and reduction. And the sixth is to transform high impact sectors for pollution-free planet. There are key sectors in which we can address to get the most out of our approach early on. And then seven, the multi-sectoral, multi-stakeholder One Health approach is increasingly through a donor lens as well as governmental lens, that it is the systemic way to address pollution. And eighth, identify, promote, and implement safer alternatives, innovation, non-pollution, and sustainable infrastructure development. And nine, the identification, and also incentivize the mobilization and of financial resources for a pollution-free planet. And 10, this raising worldwide awareness about this initiative, which we will go into the SDG summit with some sort of a pre-draft for motion for our member states, and for encouraging sustainable consumption and production. And 11, mainstream pollution prevention reduction to maximize resource use efficiency throughout UN system operations and programming. So thank you very much for your time, and I'll give the floor back to the moderator.
Sasha, thank you once again for this wonderful presentation. It was really needed for us to understand this introduction about One Health approach, and myself and our team will be very keen to find these linkages and work together, link the INSOP network to One Health when it comes to soil pollution. Thank you very much. Sasha, we have a very interesting question from the Q&A box. I think it will be nice if we can address that question from Beatrice Amanda Watts. Now, in light of the growing concern about antimicrobial resistance and the introduction of AMR genes into soil and water systems through wastewater irrigation and manure application, what specific strategies could be used to mitigate these risks? Do you have any opinion on that, Sasha, to answer?
Yes, a very good question. And this is a varied practice across different parts of the world. Of course, as I mentioned, source pollution is one key, and also treatment, pollution prevention at point sources. So pollution prevention control points at wastewater treatment systems for collective action on our SDGs 6 in addressing wastewater, and many developing countries may not have wastewater treatment systems. So it is important that these compounds can be, not only antimicrobial resistance potentially, but also many others, pathogens could be addressed collectively through a wastewater treatment. So one is that, and the other is antimicrobials from pharmaceuticals. So there are permitting in the regulatory environmental regulators, such as the U.S. Environmental Protection EPA, as well as many other countries' environmental protection agencies, can write in their permitting of waste, because whenever some operation, industrial operation has a discharge, that discharge needs to be permitted at the levels that should be addressing all of this. So that includes earlier question about arsenic, which we, through our UN work, our efforts at FAO, and our work with our member countries, such as Bangladesh, have really reduced, for example, arsenic levels to 10 micrograms per liter of water in the ambient environment to prevent ecological health hazards as well as human health hazards, because arsenic is a multi-cancer causing chemical. So with that, the US EPA actually reduced their 10 micrograms, reduced 1 milligram to 10 micrograms per liter allowed. So with a lot of the data and science that came about, regulatory guidelines and standards can be adjusted to more safer levels for addressing environment, ecological health, as well as human health. Over to you.
Thank you, Sasha. Thank you, Sasha. And thank you for this answer. One more question here from Claire Elisa Pras. Her question focuses on what are your proposed methods for detecting antimicrobial resistance as well as antibiotic resistance, and which kind of antibiotic and microbes is your target or priority to detect?
There is no general guidance on that as yet from many of the environmental protection regulatory agencies. However, there's a lot of research. Before any of these guidance will come out, at least in the United States, for example, there is a regulation that one has to collect sufficient data to address over a 5-year course to look at exposure, to look at the toxicology, to look at the treatment or technological methods to reduce and reverse the pollutant and so forth. So all of these needs to be looked at. There are some studies. I made a presentation at the Singapore International Water Week to look at a battery of research studies to bring more of that into the fore for these kind of risk assessments. Basically, the question is looking at priority risk assessments of certain antimicrobials. Right now, we're targeting reduction, take-back programs, and certain treatment systems can remove antimicrobials in the treatment system, a tertiary treatment, followed by oxidation, UV, and so on. And these can be addressed through treatment systems. So major outfalls of these pharmaceutical treatment plants that does not have provisions for discharge, they need to be looked at. And also medical professionals are reducing, and many developed OECD countries are being very mindful of prescribing antimicrobials broadly. So those are some of the work done at the health sector. In the environmental, from the livestock and crop spraying, we are trying to address this at FAO to prevent the use of antimicrobials as a growth promoter, for example. So there are various uses in which we are definitely addressing with our through our livestock working group and our livestock division. We're working in tandem with them on the whole One Health approach. I hope that answers a very complicated question. Thank you.
Thank you. Thank you. It's very informative answer. And thank you very much, Sasha, for this. Well, ladies and gentlemen, with this respect, we completed the day 2 of the INSOP meeting. Once again, I would like to thank you very much and give a big applause to our guest speakers today. They were fantastic. I think we've highlighted very important issues related to soil pollution on the recap of mapping, on PFAS, identifying, monitoring lead and mercury pollution, remediation of soil pollution in Africa. Professor Wong highlighted the issues of soil pollutants and how they affect our human health. And our Deputy Director, Sasha Koishima, concluded today's speaking points on soil and water pollution in the One Health approach. Thank you to all our guest speakers. We looking forward to collaborate with all of you and your colleagues in this topic in the near future. Now, ladies and gentlemen, tomorrow is the last and one of the most important days of the network, because tomorrow the key and the core of the meeting is to formulate the remaining working groups and launch them officially. Tomorrow we will complete the governance graph that you can see here. We have fantastic candidates that have applied already for the position. So tomorrow, I highly encourage all of you to participate, because at the end, it's you who will decide who will be the leader of those working groups. And it's you who has to tell us what we need to concentrate and focus on over the next 2 years on the activities and deliverables. So therefore, all of you have a role to play in our network. We're looking forward to see you all. Ravi, with this respect, any closing remarks for today's meetings? I think it was wonderful. Ravi, the floor to you. Ravi, please unmute yourself. We can't hear you.
Sergejus, thank you very much. You've said it all. It was a great session today, great speakers as well. And indeed, the many participants who joined us today as well. So I'm looking forward to seeing them all tomorrow as well, and also them contributing towards the selection of those lead chairpersons for the working groups. I thought the contribution that we have had from all the speakers today was absolutely outstanding. And again, it demonstrates the major challenge, significant challenge that we are confronted with from pollution perspective. Thanks so much, Sergejus. So I think we can close the day.
Thank you very much. Tomorrow we will start quickly with our Vice Chair, Dae Ho, who will do a quick recap of what has been done in the last 2 days, and then we move on to deciding and hearing your voices and your opinion on the activities and deliverables that we need to focus on. Ladies and gentlemen, thank you very much once again, and I wish you all a very good continuation of the day or good evening, and we'll see you tomorrow. Take care and goodbye.
See you all. Bye-bye.
Bye.
Bye-bye.